Greetings, guys. Let's talk about finding the surface area on um, a two-dimensional, a two-variable function, right? So first of all, let's talk about where we get the formula for this in a really hand-waving sort of way. Remember when you did the length on an x-axis, just along the axis itself in Calc 1, there was just an integral with dx, right? And then, of course, from that we can generalize. If you were to come up off of the axis and follow some other path, you could still find the length by using the arc length formula with the square root of 1 plus the derivative squared. Okay, well, in 3 space, it works very similarly. We can find an area on the xy plane, right, just a region, by doing a double integral over a region, the dA. Okay, well, we can also generalize this. A surface area integral is just going to be a double integral, just like the double integral for the area here. But since it's a surface off of the plane itself, it has a very similar format here. You can see the square root of 1 plus the partial derivative of f with respect to x squared plus the partial derivative of f with respect to y squared, and then dA. First example, we want to calculate the surface area of a piece of a plane. Now the portion of the plane is going to be defined by the region in the domain that you're integrating over, right? We're not going to integrate the whole plane. That'd be infinite. We're not going to do that. We're going to integrate over a region here that's between the x-axis and the curve y equals 6x minus x squared, okay? So let's take a look at what this looks like first. You notice that we have the equation of this plane, 3x plus 5y minus 4z equals 7. And here is that plane. Just to give you a little bit more of a view of it, we also have this version. Not quite as pretty, but you can see the way the grid interacts there. And of course the plane's supposed to extend forever in all directions. So this one's a better depiction here. So here's the plane in question. And the region that was asked was between this curve and the x-axis. Here's our, here's our xy view of that. We have this curve 6x minus x squared is equal to y. And what we really want is the surface area from the region above this. Although technically it's not all above. If you notice the little corner here does actually nick right on the inside of the xy plane there. So some of it's going to be underneath. Okay, it's going to be this region in the plane here, in the domain. That's the region that we're actually going to be integrating over. And that's the region that's directly connected to the piece that we're finding the surface area of. So let's take a look at the plane one more time. Right? That's our region. Okay, so let's have a look. Right, so there's our region. But then this is the piece that's actually on the plane. So what we're actually finding the surface area of there is that skewed parabolic looking shape on the actual surface of the plane. And yes, some of it's below, but that's okay. We're dealing in lengths and areas here. So it will come out to be a positive number still. So we're actually finding the surface area for that shape right there. Now let's get started with calculating this surface area. I know that my surface area has got to be the double integral over some region and square root of 1 plus partial derivative with respect to x squared, partial derivative, let's do it this way. Let's do dz dx and partial derivative with z with respect to y squared dA, right? Okay, so now we're set up. What I need to have is the partial derivatives of z with respect to x and y. So I'm going to start by solving for z. Here in this equation, z equals (3 over 4x) plus 5 over 4y minus 7 over 4, right? Just a quick linear solve there. And then I'm going to do the partials here. The partial derivative of z with respect to x is going to be just 3/4 here. And the partial derivative of z with respect to y is going to be 5/4. Okay, so I've got those two pieces. Let's actually set up the integral now. So I've got my double integral over some region, right? We're going to label the region in a second as well. And I've got the square root of 1 plus 3/4 squared plus 5/4 squared dA. Right? So I've got my actual integral thing that I'm going to integrate set up. Now we just need to determine the boundary, the region that we're integrating over, right? Okay, so let's take a quick look. Remember, we were already talking about that little region. Let's just reiterate. It looks like this, right? In the domain, it's this piece right here, right? This shaded portion in there. And we want to integrate. So what I'm going to do is I'm going to let y go from here to here, right? Y is going to go from 0 up to the curve, and then x is just going to go from 0 to 6. Right? Because that's this curve, 6x minus x squared. It intersects at 0 and 6 here. So I'll just let y go from the bottom to the top, and then I'll let x enumerate the end of it. Okay? So then, my outer integral is going to be the x integral from 0 to 6. My next integral is going to be my y integral, which is going to go from 0 up to the curve, which is 6x minus x squared. And then I'm integrating this bad boy right here. Well, we can simplify that a little bit, can't we? Let's see. That's going to end up being square root of 16 plus 9 plus 25 all over 16, right? Because we got the 4 squared, and the 4 squared here is going to be 16. And I just do 16 over 16 for the 1. And instead of dA, I've actually got my boundary set up here. That's going to be dy dx. Okay? Now, of course, there's no y or x dependence on this. I'm just going to pull it out. Right? I have the square root of 16 and 9 is 25, plus 25 is 50, right? And 50 I can split into 2 times 25. So this radical right here is just going to split into 5 over 4 and square root of 2 left over, right? I still got my integrals here, integral from 0 to 6, and then my integral from 0 to 6x minus x squared, and it's going to be dy dx now. So I'm just going to be integrating the y integral here, and you're just going to get y, and it's top minus bottom. So I've got the integral from 0 to, whoops. Don't forget your numbers, David. Right? 5 square root of 2 over 4. And then I've got integral from 0 to 6. And then that's going to be from top minus bottom. That's going to be 6x minus x squared minus 0. Right? Because we're integrating, we got y. And then I'm just plugging these values in for y, right? Top minus bottom dx. Of course, minus 0, right? That's not counting for anything there. So I'm really integrating the 6x minus x squared there. So 5 square root of 2 over 4. And then my antiderivative there, I'm going to have 3x squared minus 1/3 x to the third. And that's going to be evaluated from 0 to 6. Like so. All right. Now, of course, when I plug in 0 to these, right, that one's going to go away. So really, I'm only having to worry about the 6. I've got 5 square root of 2 over 4. And then times 6 squared, of course, still being 36. Then times 3 is going to be 108. Minus 6 to the third is 6 times 6 times 6 is 216, right? But really, that's 36 times 6 divided by 3, 36 times 2, right? Yeah, 72. Like so. Okay, so then 108 minus 72 gives us 36. But then, of course, 36 divided by 4 is 9. And then 9 times the 5, we get 45 square root of 2. Okay. For the next example, let's look at the area on a piece of a sphere here, right? So I've got an equation of a sphere, and I've got a particular region written in polar, right? Now remember, r equals 8 cosine theta is going to be that region in the xy plane inside of this circle here, right? Where this mark out here represents 8. So it's a sphere, and then this is the region underneath, okay? Let's take a look. As you've seen already, the equation that we're dealing with here for our function is x squared plus y squared plus z squared equals 64. And as you probably already know, that's a sphere centered at the origin with a radius of 8. Okay? What we're actually interested in is the piece of this sphere that's above that certain restricted region, right? So since we're only worried about the top half, then instead I'll just highlight the top half of the sphere there. We're interested in this, a piece of this surface here. Okay, now which piece are we actually interested in? Well, we talked about it being over the region in the xy plane where r is equal to 8 cosine theta and everything inside of that shape. So that would be this circle here.
that's wrapped around the x-axis. And then, of course, all of the region inside of it, right? That's the region that we're looking at to do this integration. Okay, so then if we bring back the sphere here, you can see that it's going to take a piece of the sphere all the way from the top down to the side. And we're only doing the top half here, so that's why it's not going to have a duality. But you can see it's going to take a piece from the top center, and it's going to go all the way down the side around this circular pattern here. Right? So this is what it looks like from the top view. Then here's the piece it's actually going to take. So if we only do that piece of the domain, we're going to get this teardrop shaped looking thing right here. That only intersects the sphere inside of that circular domain region, right? So let's take those two things away. And this is what we're actually finding the surface area of here in this particular integral.
So now let's calculate that surface area. So I need to set up my original integral here, which means I'm going to need double integral of the region, square root, 1 plus partial derivative squared, partial derivative of y squared dA, right? So I need my partial derivatives. So first, I'll need to write down what z is, right? From here, solve for z, and I'm going to get square root 64 minus x squared minus y squared. And then we need to do our derivatives. Okay, so partial of z with respect to x. Don't forget that square root is really a 1/2 power. So I'll be taking the derivative by multiplying by a half, and then it'll also reduce to a negative 1/2 power, which is going to give me a square root in the denominator here. Okay, and then the inside derivative is negative 2x. Okay, and then reducing, of course, the 1/2 times the 2 is just going to give me negative x over the square root of 64 minus x squared minus y squared. And of course, the same idea can be thought up for the partial with respect to y. I'll get negative y over square root of 64 minus x squared minus y squared. Okay, so now that I've got those two things set up, I need to plug them into this piece right here, and let's see what we can do to simplify that first, right? So just this piece right here. I've got square root 1 plus, then I've got negative x over square root 64 minus x squared minus y squared. That whole thing squared. And then the same thing for y. Okay? But of course, when I'm squaring here, I can take out the radicals from each of these. And from this side right here, notice that that's going to give me plus y squared and plus x squared from this end. They're going to have the same denominator. So I'll go ahead and write them together after you square it out. And this would be a 1, except I want to write it 64 minus x squared minus y squared over 64 minus x squared minus y squared, so that they have a common denominator. And notice at this point, the minus x squared plus x squared minus y squared plus y squared are gone, and my numerator is left as the square root of 64. Okay, so then this becomes 8 over the square root of 64 minus x squared minus y squared. All right, so let's take this piece and actually put it in the integral. So I've got my double integral over the region, and it's times 8 here. I have 1 over square root 64 minus x squared minus y squared dA. As you may have already guessed, we're going to have to do this one in polar form because we're dealing with a lot of circular objects, and also a dead giveaway is the combination of the x squared and y squared there. Side note, let's go ahead and pull that negative right here, right? Make that negative x squared plus y squared, because that's going to convert directly to being an r squared. Okay, so to do polar coordinates, I need to depict what pieces I'm using here. Notice my r is going to go from 0, right, out to the curve over and over and over again, here, here. And then theta is going to rotate this way. Technically, I could also rotate it down this way, but since we're dealing with a sphere and the top of this piece here, I'm going to go ahead and call a symmetry argument. This is actually going to resolve an issue later by just saying that the whole thing is symmetric, and I can do just the top half and double it. Okay? So it's going to go from 0, and then the cosine vanishes for the r here at pi over 2. So I'll be going from 0 to pi over 2. Let's go ahead and write that out. I'm going to have 2, because of the double symmetry argument, times the 8 that's already there. And then I've got the integral from 0 to pi over 2 for my theta. And I've got the integral from 0 to the curve. And remember, the curve is represented by this equation here. So that's 8 cosine theta. And then my integrand here, which is going to be 1 over the square root of 64 minus r squared. And then we have our differential area element, right? dA in this case is our r dr d theta that we know and love for polar coordinates. Okay, so then notice right away, this is already a substitution, right? I can right here say that I would let u be 64 minus r squared, in which case du would be negative 2r dr, right? If you're going to write out all of the different steps for your substitution there, that's fine. Okay, so that means that I'll need to balance out this r here to a negative 2r. So if I do negative 2 multiplied here, that just means I'll have to divide a negative 2 out here in order to make that work. All right, let's do this substitution integral here and get the dr out of the way. Altogether, I've got a negative 8 on the outside here, integral from 0 to pi over 2, and then my antiderivative of a negative 1/2 power, remember, because it's in the denominator, that's what this is going to be a positive 1/2 power, like so. And then I have to divide by the 1/2, so that's going to give me a times 2. And then I want to evaluate that from 0 to 8 cosine theta. All right, so I have a negative 16. Still have my integral from 0 to pi over 2. And then I'm plugging in my values here. So I'm getting square root of 64 minus 64 cosine squared when I plug 8 cosine theta into r squared. And then when I plug 0 in, I'm getting square root of 64. So that's just going to be minus the 8 d theta. Okay, well, do you notice that I can actually factor here, right? I can pull out a 64, and it's in a square root. So this piece right here, I can simplify to 8 times the square root of 1 minus cosine squared theta. Well, there's our old pal 1 minus cosine squared theta. Remember, that's just sine squared, right? So this is 8 times the square root of sine squared, theta. Be careful here, okay? Many a time we just like to wipe out things that are opposites. But the thing you really need to notice here is that this simplifies to 8 times the absolute value of sine theta. Okay? Now, since that's true, you have to be careful where your sine would dip beneath the axis, right? Well, luckily, because of our symmetry argument, 0 to pi over 2, all positive for our sine theta, right? Thanks to our symmetry argument, I can actually ignore the absolute value signs here. Okay, so then my integral becomes this. I have negative 16, 0 to pi over 2. I've got 8 sine theta minus 8 d theta. Factor out the 8 and integrate the sine theta minus 1, right? If I factor out an 8, technically it would look like this. So I can pull the 8 all the way out, and I'm just going to integrate that piece. Okay? So I have negative 128. And then this is going to be negative cosine theta minus theta, evaluated from 0 to pi over 2. Easy enough to factor out a negative sign here, and all that's going to do is make everything positive. So positive, positive, positive. Great, that works out even better, right? Okay, so then I've got 128 times. Plugging in pi over 2 into cosine gives me 0. Then into theta gives me pi over 2. Then plugging 0 into cosine, and that's on the minus side, right? Top minus bottom, so minus 1. And then, of course, plugging in 0 would give me minus 0. Okay? So then I'll go ahead and add everything up. Of course, I can't combine those, not without a calculator, right? And I'll just multiply the 128 in. Let's just do that. So what we end up with is 64 pi minus 128. Now I know that's a positive value because pi over 2 is bigger than 1. When you subtract the 1 out, right, it'll still be a positive number times the 128. So it's definitely a good valid area of something. Okay? Now something else. I want to find the surface area of the piece of z equals x squared minus y squared that's between two cylinders. So if you can just imagine, right, having this surface and you're going to have these two cylinders slicing into it, right? And we're going to find the piece of the surface that's in between the two cylinders. Here, take a look.
So here's our function, z equals x squared minus y squared. And sometimes it's easy to see the type of shape that they're talking about in GeoGebra here. And other times it fills the whole screen with all the points, and it's really difficult to get a good idea of the shape. As you can definitely tell there's a saddle there, and you can get a good idea of the shape, but not as good of one as if you were to put some more grid on the surface here. So I'll just create a parametric version instead of the normal rectangular version. And you see, it's only going to be a piece of it, but you can get an idea of what this thing really looks like if you've got some depth in it like that. So here's the function that we're looking at. Okay, now the problem is the surface of this function here that is trapped between two cylinders. So here are those cylinders. Here's the inner cylinder, here's the outer cylinder. And basically what we want is, if you see in the ring right here, we want the area of that surface that's in between these two cylinders there. Okay, so you can see, you should recognize this shape, right? The concentric circles, and then we're interested in the gap between them. That's an annulus, right? So we'll go ahead and just draw the circles themselves and then take away the cylinders. So we're talking about a section in the domain. That's an annular region. That would be this region right here of the domain. We're interested in finding the surface area from this annular domain region, right? But then we want to put that on this surface. That's the surface area we want. The annular region that fits onto our surface here. Okay, so let's see, let's take a look. There's our region, right? You can see the little piece of our function there, the blue region there, right? Okay, so then the piece of the surface actually looks like this, you see. It fits on either side like this. Fits on either side right here. And it's definitely the region in between those two circles there. You can see it fits, right? Definitely in between. And let's get a closer look at the actual shape though, what we're talking about here. So we're finding the surface area of this piece of the surface, right? From above it looks like an annulus, but when you actually get it mapped onto the surface, right, it's this weird donut Pringle, I would say.
Let's calculate that surface area. So I'm going to set up my double integral first for the surface area, right? So I've got to have my partials with respect to z. You can pick those up pretty quickly from this one. So I'm going to have my double integral over some region, right? And I'm going to have my square root, 1 plus. Partial with respect to x is just 2x. Partial with respect to y is negative 2y. And then both of those should be squared. And then dA, right? Okay. So let's simplify that a little bit. I've got my double integral over the region, square root. I have 1 plus 4x squared plus 4y squared, right, dA. Although really, instead of 4x squared plus 4y squared, right, I could just factor that 4 out and make it 4 times x squared plus y squared, right? You must see it coming, right? We already said that this is over some annular region. It's all circular, all right? So I'm probably going to be doing this in polar. Well, there's that x squared plus y squared that's going to hook us right up, right? Okay, so I'm going to have an annular region between these two cylinders, right? Which is a pretty straightforward setup for polar. I've got the angles going all the way around in the annular region, and my radius is just going to vary from 1 to 2, right? So let's set that integral up. I'm going to go from 0 to 2 pi, and my radius is going to go from 1 to 2, and then I've got square root of 1 plus 4r squared r dr d theta, right? And very similar to the last one and many other integrals that we do, I've got the 1 plus 4r squared, the derivative in here is going to require an r, and we have it at our disposal. So I'm going to set up for a substitution, right? My substitution here is I'm going to let u equal 1 plus 4r squared. So my du is going to be 8r dr, right? Well, all I'm missing is the 8. I'll do a times 8 here, and I'll do a 1 over 8 out front. Now I can do my substitution and do my antiderivative. Okay? So let's see, that's equal to, I'm going to have the integral from 0 to 2 pi. I've got my 1 over 8. Should have brought that out. Okay, I'll do it next step. And then the integral of the square root of u is just going to give me u to the 3 halves. Right? So that's going to be the 1 plus 4r squared to the 3 halves. But I'm going to divide by the new power. So I'll have times 2/3. Right? Okay. And then that's being evaluated from 1 to 2 theta. Okay? And yeah, I know we could have done the d theta as a separate integral because there was no dependence. I'm really just, working the pieces as I see them this time. It really doesn't matter which way you do it in this case. Okay, so now I'm going to have a 2/3, right? And then the 1/8. That's going to give me a 1/12. And then I've got my integral from 0 to 2 pi. And I've got to plug in these numbers here now, right? If I plug in 2 squared is 4, times 4 is 16, plus 1 is 17 to the 3 halves, right? So I've got 17 to the 3 halves minus, if I plug in 1, I'm going to have 5 to the 3 halves. And that's d theta. But again, those are just values. I can really just factor all of that out. And let me simplify it a little bit too. 17 to the 3 halves is just 17 square root of 17. And 5 to the 3 halves is just 5 square root of 5. And then I've got my integral from 0 to 2 pi d theta. Right? But we've done that one several times, right? It's just theta evaluated from 2 pi to 0, right? Which is just going to give me 2 pi. Okay? So 2 pi times the 1/12 gives me pi over 6 times 17 square root of 17 minus 5 square root of 5. Like that. Okay? Now, let's talk about this one. I want to find the surface area of z equals x plus y squared, right? Over this region enclosed by the x-axis, y equals 3x, and y equals 4 minus x. So we're talking about just finding a piece of this surface and finding the area of it. And I've got a nice semi-rectangular, it's actually triangular region in the rectangular system is what I meant. Okay, so let's take a look.
Our function is the z equals x plus y squared. It has a parabolic cylinder here. You can see it's the same parabola shooting straight down this pipeline right here. Right? Parabolic cylinder. And the reason that's happening is because of the way y squared gives you the parabolic shape, and x just basically keeps shifting it up and over as it goes through space there. Okay, and what we're interested in underneath this function is a region between 3 lines, right? Remember our lines were the x-axis, right? X-axis, the line y equals 3x, right? You can see it goes up 3/1. And the line y equals 4 minus x, right? Goes through 4, slope of -1. There it is right there. And we're talking about trapping a domain region between the three. So it's this triangular region right here, right? That's our actual R region of integration. That's the thing that's getting mapped up onto our graph that we're going to find the surface area of. So here, let's take a closer look at just the region itself, and then take a look at it underneath the function, right? You can see it's just going to be this little piece mapped up onto the function there, right? It's going to just be mapped right onto this piece of the function right here. Okay, so let's turn that on. Right. So then notice the way it wraps around the side there, right? It's definitely the right piece. It lines up with the region and everything. Okay, so this is what we're actually finding the surface area of. This triangular, it's more like a warped triangle now, right? It's sort of curved around the bottom of this cylinder. Okay, that's what we're finding the surface area of in this case.
So let's do this calculation. Now, I want to set up my integral first, right? Then worry about the region. Okay? So I'm going to have my double integral over the region R. I'm going to have square root 1 plus partial derivative of z with respect to x is just 1, right? 1 squared plus partial derivative of z with respect to y is 2y squared dA. So if I simplify here, I've got a double integral over some region R, square root of 2 plus 4y squared dA. All right. Now, given the region that we're talking about and the way that the integral itself looks right here, we'll just go ahead and stay in rectangular coordinates, right? My region looks like this, right? We're talking about this region in here. Okay, so let's set up the bounds for our double integrals here. I'm going to be integrating with this surface over this thing right here, right? And I'm going to want to go this way. If I go this way, right, I'll actually have to separate it into two integrals. So instead, I'm going to have my rectangles going this way, right? I'm going to let y be the thing that travels between the two curves. Right? Y is going to be the thing that actually bridges it here. So where do these two intersect right here? This is important because I'm going to let y go from 0 up to that point. Right? Where do those two intersect? Where does 3x equal 4 minus x, right? Well, they intersect when x is 1, right? Because that would give me 4x equals 4, so x is 1. And when x is 1, you'll see for both of them, you get y equals 3. Okay? So I'm going to be setting up my integral with the y on the outside. Right? First integral from 0 to 3. And then next integral is the x integral, right? X is going to vary in between the two curves. So it's going to go from this lower curve to this upper curve, upper, right? The further right curve. It's going to go that way, okay? So the lower bound on the x is going to be this line y equals 3x. But that's y equals, right? The integral here needs x equals. And so in that case, x equals y over 3. Just solve for x. And the same thing for the other one, the upper curve, right? The y equals 4 minus x. I just solve for x, right, in terms of y. If I solve for x by adding and then subtracting a y, I'm going to get 4 minus y as my upper bound there, right? That's what these two curves are, right? Don't forget to do that beforehand. Y equals 3x is the same thing as y over 3 equals x, okay? And then right here, y equals 4 minus x is the same thing as x equals 4 minus y, okay? And it ends up being that I use the x versions, right? So I could set up my integral. Okay, so my integral is square root of 2 plus 4y squared. And my dA in this case is going to be dx dy. Because that's the order I set it up in here. Well, yay, first integral doesn't have any x dependency inside of the radicand, or even in the integrand. So I'm literally just going to pull that out and do the integral dx, which is just x. So it's really just the top limit minus the bottom limit. Okay, so I have integral from 0 to 3, and then square root of 2 plus 4y squared, and then times 4 minus y minus y over 3 dy, like this. Okay, so let's clean this up a little bit right here. If I factor out, or actually let me just go ahead and combine first the two pieces here, the negative y minus y over 3, that's negative 4 over 3 times y. Okay? So altogether, I have 4 minus 4/3 y. To make this a little bit easier on my integration, what I'm going to do is factor it out a bit, right? Okay. So I'm going to pull out a 4/3. And I have my integral from 0 to 3. And then this thing, if I pull out 4/3, becomes 3 minus y, like this. And then square root of 2 plus 4y squared dy. Okay? All right. All right, so here's where we have to go a little bit deeper in the rabbit hole. The 3 minus y doesn't really connect very well with the radical, so what I'm going to end up doing is distributing this radical to the 3 and the y. Essentially, I'm going to be splitting it into two separate pieces. So, foreshadowing before, we would have had to do that one way, or we're having to do it this way too, right? So I'm going to be splitting that into two different integrals. Right? I'm going to have 4/3 integral from 0 to 3 of 3 square root 2 plus 4y squared dy. Okay? Now notice here, the 3 over 3 can wipe out and I'll just be left with a 4 there. Minus 4/3 integral from 0 to 3 y square root of 2 plus 4y squared dy. Right? Now, of course, this is the more straightforward one. That one's ready for, or almost ready for, a substitution. Right? We can handle that one pretty quick. This guy right here. The inside derivative would be 8y So I need an 8 here, which means I'd want to divide by 8 somewhere else, right? So I'm going to do a times 8 here in this denominator. And we'll simplify it in the next step there. Okay? All right. So I'm just doing this piece right here for a moment because that's the more straightforward integral here. Okay, so just this piece right here, I'm going to have minus 4 over 24 basically is just 1 over 6. And this is going to be 2/3 times 2 plus 4y squared to the 3/2, evaluated from 0 to 3. Now let's go over that real quick. What really happened, right? We did a substitution. I let u equal 2 plus 4y squared. Therefore, du is 8y dy. And it's to the 1/2 power. So 1/2 power went up to 3/2, and then I divided by that 3/2 power. That's where I'm getting my 2/3 from. Right here, right? And then I just have to evaluate that from 0 to 3. Okay? So the 2/3 times the 1/6 gives me 1/9, right? And then when I plug in 3, I get 4 times 9, 36. I get 38 to the 3/2. Minus, when I plug in 0, I get 2 to the 3/2. There's really not much else you can do to clean this up. I mean, you can write them as their radical forms, like we did in the earlier problem, right? That's about it. There's really not much else that you can do because the numbers there are just, pretty yucky. Okay? All right. Now the other integral, right? I'm going to leave this space so that I can come back. We want to work out that other integral so I can fill it in. So I'm going to bring that piece over here, right? Here's the integral we're actually working. We have 4, integral from 0 to 3, square root of 2 plus 4y squared dy. Okay? Now if you want to cut your time short here, of course what you could do is go look up one of the formulas in the integral charts and you can slip straight to the answer. Okay? But in case you don't have an integral sheet, let's go ahead and go through this bad boy. All right? I'm going to use trig substitution. Right? The structure gives it away. I have a square root. I have some things added in there with some squares. It's perfect for trig subs. So let's set that up. For trig substitution, I start with my triangle. Okay, here's my theta right here. And then the 4y squared and the 2 are added. That means they're going to be the 2 legs that I set up. So if I let this be 2y and this be square root of 2, notice 2y squared is 4y squared, and square root of 2 squared is 2. So if I use Pythagorean theorem, squaring these and adding them together and then taking a square root gives me the square root of 2 plus 4y squared for the hypotenuse there, right? And that's going to give me the setup that I need to do this trig substitution, right? So right here I can see 2y over square root of 2 is tangent of theta, right? Or in other words, well, let me set it up. 2y over square root of 2 is tangent theta, right? But really I'm interested in just y. So y is equal to square root of 2 over 2 tangent theta. Now I can take my derivative. dy is going to be square root of 2 over 2 times secant squared, and then d theta. And then since secant pops up, I go ahead and I notice what secant actually is, right? Secant right here is telling me that I have the square root of 2 plus 4y squared over square root of 2 is equal to secant theta. Okay, so these are important pieces here and here, of course, for the substitution. But also, this is going to give me a key also. I said also twice. Yuck. Okay? So notice right here, okay, that I'm going to have the square root of 2 plus 4y squared is equal to square root of 2 times secant, right? Another important substitution piece right there for my integral. Okay, so let's substitute. I'm going to bring my 4, right? Okay. Then I'm also going to bring my square root, which is equal to square root of 2 times secant theta. So I have integral square root of 2 times secant theta. Right? Okay. And then dy is equal to square root of 2 over 2 secant squared d theta. All right. So square root of 2 times square root of 2 is 2. Over 2 is really 1. So these become 1. And then secant times secant squared, what I end up with is 4 times the integral of secant cubed theta d theta. Right? Okay. At this point, I could choose to convert the limits. You notice I didn't bring the limits over because those are y numbers and I'm in theta land. At this point, what I'm going to choose to do is ignore the limits for a moment. I'm going to do the integral part and I'm going to bring it back into the y world. Okay? I need to do the antiderivative of secant cubed, right? That's one of those ones that you practice a bunch in Calc 2 and so on in the advanced trig methods using integration by parts, right? This is one of those ones you're supposed to know. That's equal to 1/2 secant theta tangent theta, right? Plus 1/2 ln absolute value secant theta plus tangent theta. Whoops. Absolute value. Parentheses, right? Okay. I would have put a plus c normally, of course, but I am bringing it back to using the actual limits. So the 4s and the 1/2 work out really great in our favor, right? And then I just need to substitute back in what secant theta and tangent theta are equal to, okay? So if you just come back over here and notice what those are equal to, right? Tangent theta is 2y over square root of 2, right? And secant theta is square root of 2 plus 4y squared over square root of 2. Okay? So 4 times 1/2, I've got 2. Secant theta is square root of 2 plus 4y squared over square root of 2. And tangent theta is 2y over square root of 2. Plus 4 times 1/2 gives me a 2 again. And then I've got ln and absolute value of the same secant and tangent that were over there, right? I'm just adding them in now. 2y over square root of 2, like so. Okay, now don't forget, this whole time, all the things with the y's should have been being evaluated from 0 to 3. So, right, technically, that's what I'm still doing here. I'm still evaluating this from 0 to 3, now that I'm back in y land, right? Okay. So let's finish this guy up. I've got 2 over 2 basically here, right? So it's just going to be y times the square root of 2 plus 4y squared, and then times 2. And then over here, notice these two already have a common denominator of square root of 2. So to make it easier on myself here, I'm just going to put plus, and they're over square root of 2. Okay? Now the first thing I want you to notice is that when I plug in 0, right? Plug in 0 here for y, it zeroes out that portion. And when I plug in 0 for y here, that's 0. This is 0. I end up with square root of 2 over square root of 2, which is 1. But it's the ln of 1, which is 0, right? So whenever I plug in 0, everything of that bit is going to 0. So I'm not even going to write those down, right? Those are all zeroed out. So I'm going to plug in the 3 now, right? If I plug in 3, I've got 4 times 9 plus 2. I've got square root of 38. And then I've got 3 times 2. So I've got 6 square root of 38. Right? Okay. And then plus 2 ln. And then in my absolute value here, I'm plugging in 3. That's going to be square root of 38 plus 6. And then over the square root of 2. Like so. Okay. And of course you could go through the bother of rationalizing that, but there's really no point. So let's bring the whole answer back together. I'm going to take this and bring it over here, right? And we have 6 square root of 38 plus 2 ln, absolute value, square root of 38 plus 6 all over square root of 2, right? And I'm sure there's a bunch more little small nitpicky algebra pieces you could do, but really at this point you've got square roots and logarithms all over the place. If you're actually looking for a surface area here, the good news is we did find a closed form, right? This is something that you can then further approximate with a calculator or whatever else you want to do, but it's always a good day when you can get that fully closed form on that one, messy as it may be. One more example. Okay, so this time it's only asking us to set up the integral. Always a looming sign, right? May not be something that we can actually do quite cleanly, like we were talking about in that last one. It's always good when we can find a closed form. This one may not be that way, right? You never know until we set it up. So we're talking about the surface z equals xy, right? So we have some surface. And it's over that same region that we were using in the last problem, right? So it's a interesting yet simple region where we get this triangle, right? From here to here. And this point of intersection is the point 1, 3. And we're going to be integrating, this region here. Okay. So let's actually take a look at what this really looks like.
We've got our function z equals x times y. There's another one of those saddle-ish type of graphs. You can see it a lot better than that other one, right? You can see the saddle going on here. Let me remove the plane for a second. You can see that kind of washes it out. You don't really get any structure from that. Here at least you can see it intersecting the plane and you can get an idea. Okay, so here's our first octant right here. And you'll probably get a better view of it if I just do a portion with the grid like this again. Right? So here, this is the same graph. This is just a smaller chunk of it. Right? We're interested in integrating in the same triangular region as the last one. Right? So here's my xy axis. Right? Here are my two lines from before, and we're integrating the region inside, just like before. So we get this surface here that we're actually going to be integrating inside of this region, right? But it needs to be mapped onto this surface. So we're talking about taking this piece right here and mapping it up onto here to find that surface area, or well, at least to set up the calculation for the surface area, right? Okay. So then that gives this shape right here. You can sort of see the way it's following the lines there, but it's still inside of this region right there. So we'll be finding the surface area of this guy.
Let's set it up, right? So I'm going to have my double integral here over some region. Square root 1 plus, and I need my partial derivatives of z with respect to x and y. Okay? So when I take a derivative with respect to x, right, I get 1 times y. So that's just y squared. And then vice versa, right? Partial derivative of y with z with respect to y, I'm just going to get x. So plus x squared dA. All right. Now just looking at this integral, of course I could just set up the same boundaries as before, right? But let's talk about setting this one up in polar, right? I know it doesn't necessarily lend itself to being in polar form here, right? Because it's not round. However, if you can imagine a spiral, okay, then you'd see that this very much can be something that's in polar. Because this line is coming from the origin here, you can think of that kind of like a radius, and think of it like the radius is expanding if I go in this direction here, right? As I let theta rotate, I can keep letting the radius keep hitting that line. So no, it's not making a circle, which a constant radius would do, but I can still treat this radially by rotating theta and then letting r slowly change, right? And all I would need is some sort of equation of these two lines in polar form, right? So let's talk about that for a second. Let's put these two line equations in polar form, right? The y equals 3x, this line over here, if I put that into polar, that's r cosine theta equals 3r, whoops, backwards guys, I hope you caught me, r sine theta and cosine theta there, yeah. Here it's quite easy to see that all I got to do is divide both sides by r cosine theta, right? If I divide by r cosine theta, then what I'm left with is that tangent of theta equals 3, right? The equation of any line that goes to the origin of polar is going to be related to tangent. And you'll notice tangent is equal to the slope of the line, not a coincidence either, right? So actually, this is equal to, tangent is equal to the arctangent of 3. And what that represents is the stopping point of the rotation, right? I'm going to let r rotate this way, in this direction this way, right? It's going to keep rotating until I hit this line, which will be the arctangent of 3 in radians. So we'll start at 0, right? And then we'll rotate up to that line. But I need to know what my r is going to be in each of those instances from 0 to whatever this other line is. So we need to convert this other guy as well, right? Let's convert him too. Y is equal to 4 minus x. What I'm going to do here is I'm going to add x over. So x plus y equals 4. That's r cosine theta plus r sine theta equals 4. Factor out an r. And then divide to solve for r. R equals 4 over cosine theta plus sine theta. So notice what that's giving me is a measurement of r as theta changes. So I can definitely now integrate my r's in that fashion. Okay, so let's set this up for polar. I've got my integral of theta, right, is going to go from 0 to arctangent of 3. And then my integral for r is going to go from 0 out to this function, 4 over sine theta plus cosine theta. And then my integrand, right? Square root of 1 plus r squared. See? Works out great there, right? And then dA, I'll have my r, which would go here, dr, d theta. And we've fulfilled what the instructions have actually asked for. And sure, you could start to integrate this, right? The first one here would just be a substitution, right? Easy peasy. However, once you start plugging in the other pieces of theta inside of those square roots, I think you'll find very fast that this becomes very, very clunky, junky, and hard to complete, right? Something that you may eventually have to approximate instead of getting a closed form for. Okay? Thanks, guys. I hope these examples helped you in your integrals finding surface area.